Okay? Now, in a typical full system, you'll find these components. The basic reactor, gas comes out of here, it has a lot of particulates in it. So you first run it through a cyclone, which is how you do your hot filtering. You want to get as much of that particulate out before you deal with cooling it. Again, in a historic unit, you would have a gas cooler or a radiator where you try to dump all of that heat to get it down to a temperature that's more relevant for the engine, and a temperature also that you can do fine filtering on. So then after the cooler, you will run some sort of filter, either in a packed bed or a cloth filter or something similar. Okay? Now you couldn't put that fine filter right after the gasifier because it's too hot and burn it. Okay? If it's a cloth filter, you're going to pyrolysize it. If it's a sawdust filter, you're going to pyrolysize the sawdust. So often the first time you make a gasifier, you try to make a clean gas, and you put it in a filter too hot, it has biomass in it, and you pyrolysize the filter. Okay, and then you have hot, dirty gas coming out of it.
So that's why your cyclone is always first.
That's why the cyclone is always first. And then a gas cooler if you need it. Okay. So then gas comes out of here, blower to pull it, carburetor to mix it, and then it goes in the engine. Please do that. Oh, no, I didn't save it. Okay, so what we've So one of the core pieces of work we've been doing is trying to recover all of that waste heat that's coming out of the gasifier and both return it to the reactor as well as cool the gas down to engine-relevant temperatures without having to have an extra radiator cool it. Again, we think to get this stuff relevant, we need to get it into the smallest of form factors as possible with the least number of components and really do the core work in a highly optimized, dedicated reactor and don't take on all these band-aids before and after. Okay? So, what we've ended up with is the Hot Toddy, which is a series of heat exchange vessels that in stages mine heat out of the outgoing gas and return that to appropriate temperature points in the reactor. And then secondly, using all the waste heat that's coming out of the engine to have a fully external source of heat to put into the reactor. Okay? As we know, an internal combustion engine is really a heater with a small byproduct of mechanical energy. And we typically are running in the realm of 20% efficiency to mechanical energy, and we have 80% being lost to heat. And we've gone through all sorts of exotic regimes to try to do something useful with that heat, to getting it to electricity or shaft power, and they're famously very difficult things to do. That's why we just accept a very low energy efficiency engine. But if you're running a gasifier next to an engine, now the waste, the raw form that the waste is coming out of the engine, heat, is exactly what you need in the gasifier. So these heat recycling systems become much easier if you have off of the engine, if you have a gasifier sitting next to it. And really, you can consider the engine as part of the gasifier. The engine is a combustor. It's making a bunch of heat. And what does a gasifier need to process its fuel? What does a gasifier need to break down the fuel? It needs heat. Okay? So we really treat the engine as part of the combustor in the gasifier. Okay? And get all of the heat that's coming out of it back into the gasifier to do useful work. Okay? So how does this set up? Here's the basic GEC. We have the air preheating system, gas cooling system, which is pulling the first stage of heat out of the outgoing gas. We get an exit into the cyclone about 200 to 200 C. We take it through the cyclone. Ignore the steam coil for the moment. Comes out of the cyclone under 200 C, which is a perfect temperature for drawing. So the second stage of use of the outgoing gas is for drawing. We do a double-walled heat exchanger vessel at the base of the hopper, and we take that hot gas, outward-going gas, pass it back and forth through that double-walled vessel, putting heat into the fuel vaporizing the water out of it, which then can run a moderator condensing cycle on the top. If you vaporize fuel here, or excuse me, vaporize water here, it's going to travel upward by convection, come over, and when it meets the cool walls here, you'll get condensation on the walls, and that water will pass down the walls to the base, where you can put a little collecting ring and then pull the water out of the reactor. This is called a moderator hopper. These are a very old idea. So you let a passive convection and condensation circuit operate inside the vessel, and you put a collection ring at the base to pull the water out. Okay? So by using the outgoing heat from here, we get gas coming out of the top here, in the realm of 100 C. Okay, without any radiator. So then we take it from here. There used to be a filter up here. It's now the larger barrel filter. You take it through here through some sort of hose that can radiate heat. It goes in the filter. It radiates more heat. So as you've lost that remaining heat through the filtering system, you're now down to the temperature you can take directly into the engine without any dedicated cooler or radiator. Okay, so you've lost that component. So that's the gas outgoing side. Okay, we deal with all of the water vapor, the water load in here. So by the time the fuel's got to here, the drying is completely finished. We've eliminated the drying load from the gasifier. Okay, but we haven't eliminated the steam from the gasifier. Or we can or can't, depending on whether we pull the fuel out or the water out of the moderator. Okay, we have so much extra heat in this thing that though it's set up for a moderator, we don't even run it. We just let the steam go into the reactor.
When you say that you completed the drying cycle, what's the moisture content that you reduced to optimize the gasifier?
We don't know the maximum amount of moisture we can put in, and that's what the steam coil is here. To the degree to which you can deal with water in the reactor, you want it. More water vapor in the reactor is going to break over the char, and you're going to get a higher fuel quality out. So why these things have such poor energy density is because you're combusting inside the reactor to get your heat, but you're combusting with oxygen or with air that's 80% nitrogen. So you have a bunch of nitrogen in the system, which is diluting your outgoing fuel gas. So you want to minimize the amount of combustion that you have internally in the gasifier. So if you're bringing in a bunch of other heat into the gasifier, you can combust less internally to get to the amount of heat you need. If you have an infinite source of heat and you can actually transfer it into the gasifier, you don't need any burning in it internally, which is how an indirect gasification system works. Okay? There's also coal gasification systems where you heat the coal, you make the red hot char bed, and then you pass steam across that char bed, breaking it into hydrogen carbon monoxide, pulling the energy out. You get the fuel gas coming off, and when you've dropped the temperature down to where the reaction bed starts or stops, you then transition to a second reactor that's been heated up in the interim. These are called carbureted systems. This is how town gas was made historically. It's two reactors side by side. You burn one and get it really, really hot, okay, pass steam over it, generate your gas just off of the heat that's in that char bed. So you get full hydrogen and CO without any nitrogen in it. And while you were doing that, you were burning another one to get it up to temperature. So when this one's run out, you now switch. You make your gas out of this one and then burn this one. So you go back and forth. So that gets the nitrogen out. Okay? So you can go in that direction by adding other heat in real time through heat transfer solutions. So that's the process that we're on here, is trying to maximize the amount of heat that we're putting into the system such that we minimize the amount of combustion in the system.
You were pointing to a steam coil. Where is that?
Okay, so we actually have more heat in the outgoing gas than we can take into the air, and we really have too much to finish the drawing also. So, and we want to be able to we want to get the maximum amount of water or vapor into the reactor that we can handle to increase the fuel quality. The problem is, at different pull rates and different gas flow rates, the amount of water you can handle is going to vary, because the amount of combustion and temperatures achieved inside is going to vary. So ideally, you would like to dynamically control the amount of water you put into the reactor in relation to what you see as real-time temperatures inside the reactor. Okay, you can say, oh, you can't say like, well, fuel at 15% is perfect. Well, it might be a nice average, but there's times where you, at very high loads, you can put in much more water, and if you're trying to run a very low load, you'd like to have less water. So ideally, you are variably injecting the water in relation to what the reactor can take. So as soon as you have a control system and you can measure the temperature inside the reactor, and you know what the minimums are to complete the tar conversion, you can now control the injection of water. Okay, and that's the next step that you can see here. We haven't done it yet, but the notion is you use the heat in the cyclone, you wrap it with a copper coil to raise steam, and that steam is then taken in through the air inlet to the degree to which the reactor can handle it. So you measure in real time the critical temperatures in the reactor. You maximize the amount of steam that you put into it until but always keeping it above the minimums you need in the reactor. So this is part of the point of all of the testing and documentation work that we were doing, or Bear was doing last year. It was all about to understand or trying to relate correlations between temperature inside the reactor and tar that comes out of the reactor. Okay, and we've now completely formalized those numbers such that we can say if we see X temperature at the critical point in the reactor, we know our tar production will be Y. Okay? So with that raw number as a temperature, we now have a very simple to measure value that we can use to determine how much water to put in the reactor. Okay.
Your heat exchanger for your steam is copper on the outside of your on the cyclone, it's wrapped on the outside. Or
That's what we've thought. I mean, there's many better ways we can do it, but I think it'll be enough just to get it on the outside.
Just to get it up to steam.
Yeah, but we might have to do it on the inside. We might have to do some other exchange. I don't really know. So the other thing you get out of that is once you have a place to put water in this reactor and you can do it mindfully, you now have the potential to responsibly run a water filtering system. Again, the problem with the water filtering system is the water is a much better filter always than the dry methods, but you end up with this mess to deal with. Okay, even if the gas is clean, there's going to be junk in the filter water. So, but if you can put it back in, if you can raise it to steam, put it back in the reactor, now you have a place to put the filter water. So it becomes more responsible and thinkable to run water filtering systems, which perform better. They can happen in a smaller space. It's generally a more efficient filter, and you can now have a water source for your reactor. So we'll probably be doing some water-based filters that are really the water feed for this steam system. Okay, those are relevant in hot climates. You can't run them in cold climates where it can get freezing. So that's the other thing. Yeah.
You
Okay.
have a tar buildup on the inside of the exchanger farm?
Yes, that's
That's the issue.
That's the issue. So you still can't make dirty gas. Okay. So I mean, if you're this filtering scenario, the current filtering scenario and the current architecture is premised on you have clean gas, and if you don't, the filter's not going to be enough. So we have to make clean gas. But even once you've made clean gas, you're going to have particulates in it and soot and other things that you can filter much better with water than you can dry stuff. Okay? And to the degree that you start wanting to look at liquid systems, getting a liquid system on top of this thing, you need very, very clean gas, much more than you're going to do with just basic packed bed filters. So an engine, once you get rid of the tar, the engine can tolerate a lot of soot, doesn't really care, but that won't work if you're dealing with a liquid system.
So what do you think you're going to put the water injection system in there by next summer?
Well, all of the control things to do it already exist. We just haven't had time to do it. I mean, the GCU is set up such that you can measure all